Welcome, everybody. It's my tremendous pleasure today to introduce our next distinguished lecturer in the DLS series for the Allen School. And with great pleasure, I want to introduce Jennifer Rexford from Princeton University. I think a lot of us who do networking systems know Jen very well. In fact, I think my guess is that if you do ask some of our younger colleagues who they want to be when they grow up, in terms of just sheer impact and Jen's service to the community and how accessible she has been to everybody, Jen probably would be the top name that occurs to most of us. But for those of you who don't know her, I think she's currently serving as the chair of Princeton University, has won in networking and computer science all the awards you can imagine, including the ACM Grace Murray Hopper Award for Outstanding Young Computer Professional, ACM Athena Lecturer Award, Harold and Notkin Research Award, ACM SIGCOMM Award, IEEE Internet Award. I'll just stop here and instead, in the interest of making time. But this is also a talk that have been really looking forward to, and Jen's been driving this type of work for a bit. So welcome all. I'll let her take it from here.
Wonderful. Thanks, Ratul. It's a pleasure to be here, and I look forward to the time we can all be together in person. So the internet is really a remarkable success, a research experiment that escaped from the lab during our lifetimes to become a global communications medium that we use pretty much every day for everything, and all the more so during COVID. And part of the brilliance of that was the decision of the early designers of the internet to keep the inside of the network simple with a best effort packet delivery model and put a lot of the functionality at the end host computers that we connect to it at the periphery. And in particular, I think an important lesson to take away from that early design decision is that where you put programmability in the computers at the edge of the internet determines who can affect change and where. And unfortunately, though, what we've seen is that while there's innovation above the internet and alongside the internet and the devices we connect to it, the applications we run on top, and the media we connect to below, the designers of the internet didn't really plant the seeds for the internet's own reinvention. The inside of the internet is quite the opposite, not programmable, hard to change. And in particular, inside the internet, we traditionally see highly specified devices that go through slow standardization processes with standards often baked into fixed function hardware. Equipment that's closed or the software and hardware are bundled together, both created by the vendor, that offers often low-level Baroque interfaces for configuring the device. And as a result, relatively few people have been able to innovate. And even the people who own the equipment often can't introduce new features without going through their vendor, with long delays and difficulty making sure their competitors can't just similarly use the same features. Yet I would argue the inside of the network does need to change because it's the part that determines whether the network's reliable, secure, performant, cost-effective, preserving of user privacy, and more. And so it's really quite difficult to make those changes. And that's what I want to talk about today. And I would argue it's good for the internet that it be more programmable, but also the research community. You can see plenty of signs in the networking and systems community that we're really desperate to innovate on the inside of the internet. We work on all sorts of platforms for programmable packet forwarding in hardware and in software, interfaces to that hardware, software that runs above that to control how the hardware works, and research programs that have run over the last several decades under many different guises, but all looking in different ways at how to add functionality to the internet and make it extensible over time. And we've designed and developed lots of different test beds over the years that allow us to experiment with programmability and to show what it can do to enable innovation inside the internet. So what I want to do in this talk is look at when we try to add programmability to the network, something we've been trying to do for a long time, what works and what doesn't, and when does it work and why not. And what lessons have what lessons have I learned along the way? And I'm going to structure this as a sort of 25-year retrospective of research I've been involved in and research I've observed from the perimeter. And the lesson of the talk is really twofold, and I kind of call it keeping it real, which is the idea of having a balance of ambition and pragmatism. Ambition to think of new conceptions of how the internet might work, and pragmatism to really actually make it happen in practice. So sometimes requiring a little bit of a compromise in terms of the amount of ambition of the work. So there's going to be two main themes to that, and they seem in conflict, but they're both really important. One is really staying in touch with reality, using real data, real software, trying to satisfy real users, being aware of the new technologies that are coming and the market pull that might make it possible to add more programmability to the network. So think of this as changing what you can. sometimes not as much as you'd like, but what you're able to given the current moment. And yet, obviously, if you stop there, you end up in sort of a local minima where you're not able to make the long-term change you want. And so there's also another side to this of trying to shape future reality, creating new artifacts that others can build on, building a community of researchers and practitioners who use those artifacts, and do what we can to enable new kinds of change. And as I mentioned, I'm going to do this as a 25-year retrospective, and I'm going to ask you to humor me for a moment while I wax poetic about graduate school. And I'm doing that for a couple of reasons, because there are a few things from my grad school experience that inform what I do today, and also some cautionary notes too about some things I wish I had done a little differently. And then I'll talk a bit about the work I did at AT&T, where I worked for 9 years before coming to Princeton in 2005. And I'll talk a bit about some work that happened in the academic community while I was in industry, and also things I worked on and then continued to explore when I came back. So, but first, I'm going to take a few minutes to talk about grad school. So when I was graduating from college in 1991, parallel computing was a very popular topic. Moore's law seemed to be coming to an end. Maybe not quite yet, but we thought it was. And we were very interested in harnessing multiple computers together to work as one, to solve problems a single computer couldn't solve fastly enough. And we looked at ways in the research I was doing in grad school at how to build multi-computer machines that could combine multiple processors and simple networks together. And in that context, I was really interested in how to support diverse workloads, whether best effort or real-time applications, lots of different kinds of scientific workloads that would put different strains on how routing and flow control were done. And so I worked a lot on the programmable router hardware that existed inside these parallel machines to allow the routing and flow control to be customized to the workload. And in fact, multiple virtual networks to run concurrently, each handling a different workload and each handling it differently. And so one thing you're going to learn from this talk is I'm a one-trick pony. I've been working on this problem for 25 years. What kind of network I'm doing it in changes, but I continue to work on largely the same things. And as you'll see, I worked on the heels of many failing technologies, particularly before I decided to work on internet-related topics. So the punchline is, and you probably already got it from my previous slide, when we thought Moore's law was over in the late 80s and early 90s, we were wrong. It wasn't true. And it's apparently true now, but certainly 25, 30 years ago, it wasn't. And so in the end, a lot of the parallel computing work struggled to keep pace with the next generation of silicon. Sure, you could have a 10 or 100 or 1,000 processor machine, but it was still slower than the next generation single processor machine. And the networks weren't really the hard part. It was the applications that were built on top, hard to extract the inherent parallelism. So I used to go to parallel computing companies and they would, conferences, and the companies would give us mugs. And I have a shrine now of the mugs of now defunct parallel computing companies that gave me mugs at those conferences. But the second challenge wasn't just that. It was also really hard to evaluate the research I was doing. There weren't real applications. The custom chips we were designing took a long time to fabricate and evaluate. And so it was very difficult to evaluate our ideas realistically. But I don't mean to be so negative. I think we all hate our thesis by the time we graduate. That's sort of human nature. But I think in some ways I perhaps should have been more patient because Moore's law is coming to an end now. And modern data centers look a lot like the multi-computers that we studied back in that time. But there were some important lessons I got from that work that you'll see come up over and over again in the rest of the talk. But right around the time I was having this crisis about my thesis, the World Wide Web exploded. And I started to see around me everything that was missing in the work I was doing on my thesis. Real applications like the web, real data, people starting to do measurement studies of workloads and protocols on the internet, real users that were struggling, system administrators, network administrators. I started to try to learn more. I started reading the Larry Peterson's First Generation Networking textbook where he talks about the X kernel. I started reading the code, like, wow, there's real code. I can learn how things really work. And then I started to learn about asynchronous transfer mode switches, which were also starting to be a common topic of research at the time. And they looked a lot like multi-computer routers. And I saw there a segue through some internships at AT&T where I could start to take what I knew about multi-computer hardware and apply it in a new context. So long story short, after I graduated, I went to AT&T and I continued working on asynchronous transfer mode networks. And if you haven't heard of these before, don't worry, because this slide will start and end this thread in just a moment. I looked at how to do packet scheduling, packet shaping, routing, signaling. And then, we got to carry some traffic over these networks. So I looked at how to carry internet traffic over ATM. And then I switched to an area of research I've been in ever since, which I call IP not over ATM or the internet. So during this 3-year period, I too was working on a technology that didn't really make it. But again, there's some lessons here. In particular, when I started trying to get real traffic data, I would submit papers to conferences and the conference committees would say, hey, you work at AT&T, can't you like get real traffic data and not do synthetic simulations? And so I started trying to get the data, and I realized it was actually really hard to measure an operational network, to know its topology, its traffic, its configuration. And I started to realize there might be an interesting research program to have there, just in getting the data itself. And then second, IP over ATM, the way it worked is it would take something like a web download or other kind of communication over the internet and would associate it with a circuit that would be routed through this asynchronous transfer mode network. The first packet of a transfer would trigger the creation of state throughout the network that would carry the rest of the traffic of that conversation. And we'll see these ideas appear again in software-defined networking when we fast forward a few years. So not all is not lost. The technology didn't make it, but some of the ideas still end up being relevant. So finally, in the academic community at the same time, there was a struggle going on to think about how to make networks more programmable. In the same period, I was working on ATM networking, and it was motivated by the fact that the internet was becoming this success that we couldn't change anymore, that we wanted to put custom functionality in the network. We wanted to do more experimentation, but it was really hard. And there were a couple of different models of thinking about this, one called capsules, where the packets themselves would carry the code that would run on their behalf in the devices along their journey through the network. And another more pragmatic model called programmable routers, where the routers would have code that could be invoked when the packets arrived. And there are a lot of interesting contributions here, and many of these have come full circle in the last few years. Certainly the high-level themes of programmability as a way to enable innovation, demultiplexing packets to software programs, and the vision of a unified architecture for middle boxes, something the community is still really actively working on. But from my perspective, I wasn't involved in any of this work. I was watching it from the sidelines, and I was really preoccupied with who is the programmer? Should it be the end user, or where my interest was, the network administrator? And what about speed? A lot of the early work on active networking focused on functionality instead of performance, kind of like I did in my PhD work, where in the end it was hard for flexibility to win out over a higher performing but less flexible network. So those were the two things on my mind. So as I started getting data from operational networks and realizing that there was a lot of richness there, I found what I was missing, which was a real quest for reality, real users, people with pain. And advice to particularly the grad students here, if you can find someone in pain, usually there's an interesting research question there. And network operators were in pain and they had nobody listening to their war stories. And so I became a very empathetic person who listened to network operators tell war stories. And I learned a lot from them. And I also got a lot of really useful data to try to evaluate my ideas. And then I started to think about programmability, but of a different sort. Programmability above the network, not inside it, where we could collect measurements from the network using whatever data we could get, analyze or optimize it from outside, and then go back and affect change in the network by configuring whatever knobs we might have available to us. Very pragmatic, but deployable immediately and able to solve real problems. Like, how can we optimize the flow of traffic in the network? How can we do maintenance on equipment in the network without causing an outage in the process? How can we detect and block denial of service attacks? So programmability above the network, programmable network management, if you will. And again, taking existing routers as a given. So pragmatic, changing what we can, not what we can't. Even at AT&T, one of the biggest companies that buys network equipment, wasn't allowed to change the software, let alone the hardware of the network equipment. And so we took the existing routers and protocols as a given. So I want to give just one anecdote of a kind of problem I worked on there to give you a sense of what it means to bolt network management on top of a network that was never designed with that in mind. And it's a really simple problem. The routers compute the paths through the network based on shortest paths. They propagate information about the weights on links in their network topology, and each compute shortest paths and forward traffic out the links that will lead it along the shortest path. So traffic entering here on the left, going out on the right, will take this path that goes through the links with weights 2, 1, and 5, because that's shorter than the path below of 2, 4, and 3. So What's interesting here is the network is solving the problem of computing shortest paths, but the network operator is solving the opposite problem. How do I set these numbers so that the routers compute the paths that I want? So in a way, the design of these protocols induces a network management problem to tune the link weights to get what you want. And in particular, what they wanted was to minimize congestion. So we worked for a long time on ways that we could help the network administrators do this. Now, how were they doing it before we started helping them? They would say, gee, this link is congested. I'll crank up its link weight. That it would no longer be on all the shortest paths it was before. And in particular, some traffic might move to an alternate path. But they were doing this willy-nilly, tweaking link weights, sometimes having it not work the way they expected, twisting it back quickly before the problem was noticed, and so on. And so what we did was give them a method for doing this where we could measure the network, optimize the weights, and reconfigure them accordingly. And so we did a bunch of different work on collecting the offered load between the endpoints of the network, the traffic matrix, if you will. That's actually a hard problem in its own right. Work on optimizing the link weights, and finally on making changes to the link weights without causing transient disruptions. Interestingly, the original problem is a really tiny piece of this. In the end, there was a lot of work in modeling exactly how the protocols work. It's not quite as simple as I made it sound on the previous slide, and a lot of work on how to collect the data and change the network without causing disruptions. And in particular, one thing I did at this time that I wish I'd done much earlier in my career is I started working the night shift in AT&T's operations center as I started using our tools. And I learned some really hard-won lessons by doing that. In particular, the first time they tried to use our tool, everything didn't work because the topology data was wrong because it had been entered incorrectly into a database. And the configuration of the link weights we recommended violated some rules they had about an ongoing voice over IP trial in Texas, where they weren't allowed to send extra traffic to Texas, even though we thought it was a good idea. And so in the end, our tool had the wrong input data, gave the wrong answer, and they didn't use it. But other than that, we were on the right track. So we worked with them over a period of many years to get to the point where we could model the kinds of things they were worried about. And eventually the tool started being used really frequently in AT&T's network. But as we really learned from this, that we weren't always focusing on the problem that was actually the one that was actually important. So I think before I go on, maybe I'll pause here. If there anyone that has any questions about what I've said so far, feel free to either just unmute and ask, or you can put things in the chat. So we continued working in this way, taking lots of network management problems and figuring out the measurement, the optimization, and the control that one might want. And as the years went by, we developed a lot of stack on top of the underlying network. The data plane that we couldn't change, that would forward packets based on a forwarding information base installed by a control plane that we couldn't change, running lots of protocols, and then finally management tools that we were designing that would read the dials and tweak the knobs. And we became anxious as we did this, that every time we solved yet another problem, we're adding more and more code. And it was more and more complicated because we were having to invert and model everything the control plane software was doing just to coax it into doing what we actually wanted. And we began to be worried about where this would lead, which is to a really complex and potentially buggy set of code. And so we started to think, what can we do about this to make this more fundamentally better? Now, when I was at AT&T, it was common that people that worked on the phone network would tell us stories about how much better it used to be before the internet. And whenever they told us these stories, we would often roll our eyes and be like, oh, it's the bellheads reminiscing again. They don't understand about the internet and how it's different. But this was one time where they were right. So they started talking to me about this thing called the Network Control Point, or NCP, that existed in the early 80s. And it's a really fun set of papers to read from the early 80s, where the phone network went through this exact same problem, where people wanted to add more features, caller ID, call waiting, call forwarding, and couldn't really do it with the legacy equipment that was widely deployed. There wasn't enough processing resources, and the model was going to not be backwards compatible. And the idea was, well, gee, what if we had a logically centralized server that would make all these decisions and then just tell the underlying existing equipment what to do? And I thought, whoa, that's a really cool idea. Separate control from action, and you can get, scalability and flexibility and more. Sounds like software-defined networking, right? It's pretty much the same basic idea, except applied to a different network model than the internet. So begin to wonder, well, in an internet context, what would that same idea look like? And many of the problems we've been solving were network-wide routing control problems of one sort or another. Which way should the traffic go? When should the routes change? When should the routes block the traffic rather than deliver it? But the challenge here is going to be, how would we do that when we can't change the equipment, when we're not allowed to change the hardware or the software? And so the idea was that maybe we could just trick the routers into swallowing the answers to whatever we wanted them to compute. And in particular, a lot of internet service providers use a protocol called BGP, or Border Gateway Protocol, for the routers to learn from their neighbors how they're going to reach remote destinations, whether it's from neighboring domains or even amongst the routers in a single domain. And so we thought, hey, what if we could have the neighboring routers of AT&T, the Verizons, the Sprints, and so on, talk to a computer rather than a router? They don't know any better. If we speak BGP to them, they'll be happy. And what if we compute the answers we want and shove it down the throat of the router? Give it only one choice, it'll pick that choice. And so what we did was design a server that we called the routing control platform, in sort of deference to the NCP that inspired the idea, that it would take as input all the externally learned ways to reach destinations on the internet. And as output, it would compute the forwarding tables that we would like the data plane of all the routers to use. And we would do that without changing the routers and without getting any cooperation from our neighbors, by using this protocol that wasn't really designed for this purpose, but can do well enough. Pragmatic ambition again. And one thing that's really interesting is, in the end, you would think a network with hundreds of routers couldn't have all of that computation replaced by a single computer, but in fact it can. This is a gift from Moore's Law. Moore's Law actually was the gift that kept on giving. The server that we used was, significantly faster and had more memory than the processors and the router that was built just a year or two before. And a lot of the computation routers do is redundant. Many routers in the same network compute very similar things, and so we can amortize a lot of the computation. And then if you can put all that work in one computer and you need to replicate it for reliability, you don't have to have complicated protocols to do that, because you can do the entire computation 1, 2, 3, or 4 times. No big deal. You don't have to make a very complex distributed system to make this work. You just need kind of dumb replication. And so in the end, we found a single computer could do the work of all the control plane of the network and use that legacy control plane just to force the routers to pick the answers. And so AT&T deployed that in their backbone and ran a bunch of applications on it. And in particular, because we really wanted this to get deployed, we started looking for compelling use cases. And we tried to find multiple business units in AT&T that would like this idea, because we thought any one of them probably wouldn't be enough to get the network operations team to bite the bullet. And the 3 that were compelling at the time were security, because denial of service attacks were starting to be a serious threat; virtual private networks for corporate customers who wanted more control over their routing; and interactive applications like online gaming that were suffering outages when AT&T did planned maintenance. And I'll talk about the third one in just a little bit of detail. It's sort of a less glamorous application, perhaps, but it makes it really easy to illustrate how the solution worked. So at the time, when we were working with the night shift people, we found what would happen when they did planned maintenance was Sony EverQuest, which was an online game at the time. Every time AT&T did maintenance, all the video game players would die because they would lose connectivity with the server for just long enough that the server would kick them out. So the problem the network operators wanted to solve was to adjust the network, maybe to do traffic engineering or to do maintenance to make the network better. But ironically, they were making it worse just long enough to disrupt an interactive application. What's the problem here? They want to take, let's say, egress 1 here down for maintenance. But packets are in flight and will get dropped on the floor if you just turn off egress 1. Now, this is actually fairly maddening. The network operators know hours in advance. I would work the day shift with people 12 hours earlier who would say they're going to take this router down. And yet there's no way in the protocol to to prepare the rest of the network for the fact that you're going to take this node offline. So the idea is very simple. You have the server tell all the other routers in the network to start using a different way to reach this destination, say egress 2, while egress 1 is still up. Only after all the packets in flight have drained do you take egress 1 down, safe in the knowledge that nobody's relying on it anymore anyway. And that's it. Note here, we don't even need to use the RCP for the vast majority of routing. We're just using it to override the normal handling of just the destinations that are reached through a particular router. And that application ended up being the first one we deployed, so much simpler than working backwards to bend over backwards to get the routers to do your bidding. It's better just to tell them what to do. So around that time, the folks at Stanford and at Carnegie Mellon were working on a project called the 100 by 100 project. Hui Zhang at CMU and Nick McEwen at Stanford. And AT&T, our group at AT&T was involved too. And Hui came and did a sabbatical from CMU at AT&T. And we told them about the RCP. And his reaction was really interesting. He said, this is actually a really good idea. Maybe this is the right way to do things, even if you had alternatives. And we were very apologetic, like, we're not allowed to change the routers, so we're doing this kind of hacky thing. And he said, maybe that's actually the right way to do it, even if you are allowed to change the routers. And he gave us sort of a dose of academic ambition, if you will, to be a little more proud of what we were doing. And to start thinking of, if you really could change the software and the hardware, how might you do things this way, the right way? And we came up with a high-level architecture we called the 4D architecture. And you can tell it's from this time period because of the very low-resolution fonts in this picture, which I decided to keep as is, just for historical accuracy. So the idea is basically 3 principles. We want to have network-wide visibility that satisfy network-wide objectives and exercise direct control over what the packet forwarding devices do. And the 4 layers I mentioned here make that possible. The data plane is going to forward the packets. The discovery plane is going to do measurement of the topology, of the traffic, of the performance. The dissemination plane is going to allow a central decision entity to collect that data and effect direct control over the devices. So that was the high-level idea. And you could view the routing control platform as a primitive version of this, where we weren't allowed to change the data discovery and dissemination planes and had to hack our way through it. But that led to us and others starting to think more about how would you actually do this right? So around this time, I leave AT&T to go to Princeton. But this is the last thing I worked on before leaving AT&T. So I moved to Princeton, and I wanted to really pop up a level. I thought it'd be fun now to start thinking about networks that are not bolted on with network management, but are inherently easier to manage. To essentially re-ask the questions I've been working on at AT&T, but with more freedom to change how we answer them. And I also was still thinking about, even though I had left industry, I wanted to still be thinking about ways to make my research real. And I got connected with Larry Peterson, who was already at Princeton at the time, working on Planet Lab with a number of people that are on this call. And he was also thinking about ways to make it real. And he was thinking about how active networking didn't make it, but the idea of programmable routers that could run code, that packets could be demultiplexed to code in the middle of the network was a good idea. And Planet Lab was a research platform that embodied that idea and was widely deployed. But it was really used primarily for distributed systems research and for network measurement, not so much for the kind of things I was interested in. And so we started to think more about how could you build a virtualized programmable network for network level activities. Think of this sort of a pragmatic take on active networks. So at the time, a lot of people in the community were grappling with how to enable greater experimentation in networking. Should we build standalone test beds? Should we deploy ideas in our own operational networks in our campuses and so on? And Nick McEwen's group at Stanford did a really cool project called Ethane that was essentially a 4D solution for enterprise access control, where you would take the first packet of every flow, every connection, every conversation, if you will, send it to a controller and ask, should I let this traffic in or not? And then reactively install into the data plane the access control policy that would either permit or deny this traffic. So very much a similar kind of 4D approach, but focused on a completely different set of problems than we were thinking about. And they started to think, actually, this one application is just one of many that would like the ability to see some of the traffic in the network and tell the data plane how to forward the rest. Wouldn't it be nice if the first packet in a flow, not unlike IP over ATM back from a few years ago, what if we could just look at that first packet and then install rules? And at the same time, in parallel, data centers are starting to happen in industry, and there's starting to be a bunch of vendors, Broadcom, Intel, Marvell, and others, creating merchant silicon chipsets for packet processing. So you don't have to be one of a small number of large companies that fabricate your own router equipment. Now, a lot of companies, HP, Dell, NEC, and others, were starting to be able to make network equipment because they could buy the chips rather than build them. So OpenFlow originated out of Nick McEwen's group at Stanford as a general interface to what the existing merchant silicon chipsets could do. Pragmatic, no changes to the hardware. But now we can make the control plane programmable because the interface to the data plane is standard and open. And for me, a great lesson from OpenFlow was it was simple enough to explain to non-networking people. Rather than talking about OSPF and BGP and all sorts of routing protocols, I could say, hey, all of the device is doing is a packet comes in, you take some of its bits and you match it against a rule where each bit can be a 1, a 0, or a wildcard. And based on that match, you do one simple action: forward the packet, drop the packet, send it to a controller. All the marketing terms we use in networking are just this in many different guises. A router matches on destination IP prefix and forwards. A switch matches on MAC address. A NAT matches on multiple fields, a firewall, etc. All of them are just different variations on matching on some bits you parse out of a packet and doing a simple action to the packets that match. And so it became possible for me to start talking about networking to a much wider set of people that don't already have a lot of knowledge, in particular programming languages researchers. But most importantly, now the control plane can be programmable because the interface to the data plane is open. And a group of us started working on standardizing the OpenFlow protocol and the OpenFlow interface really, and also deploying it in our campus networks to run experiments and also to enable new services. And I started talking with our campus IT staff to understand where they felt pain. Now, as I mentioned, programming languages was a real opportunity here because now we've got a much more standard interface, much more intuitive than the things I was working on at AT&T. Jonathan Smith at Penn, who had worked a lot on active networks back in the day, reached out to me and a few other people suggesting that the programming language faculty member and the networking faculty at Penn, Princeton, and Harvard should do a project together to think about how we could do programmable networks again, going back to the work on active networks, but with the advantage now of new use cases, new hardware, and the involvement of programming languages researchers right from the beginning. And so I became acquainted with my own colleague, David Walker at Princeton through introduction by Jonathan. And we started looking at programming abstractions on top of OpenFlow, building on top of the early software that the Stanford group had developed, creating real applications, finding it was very painful to write them, and reflecting on that pain and finding ways to make the pain less. Now, Nate Foster, who's now at Cornell, did a postdoc with me and Dave, and we started doing all this work together. And we realized that what was great about OpenFlow is it had the things we wanted for a 4D architecture: network-wide visibility, direct control, and a simple abstraction of the data plane. But really, it wasn't a linguistic formalism. The interface is still really low level, installing rules with ternary matches and priorities and actions. The functionality really tied to the hardware, the resource control of how many rules you can install and when, being quite constrained. And it gets worse, because if you want to write modular applications, that's very difficult because there's one rule table, and yet you want to do many different things. So what did we do? Well, we started thinking about this control loop again. We came up with measurement abstractions based on SQL, where you could query the statistics in the network, abstractions for composing applications together, so you could have a web load balancer that then has its packets routed and monitored. And we came up with compilers to do that, and also ways to affect control in the network without causing transient disruptions. And I'm not going to talk about all of these, but I just want to talk about the last one because it harkens back to the example I gave earlier about Sony EverQuest and the outages that existed in AT&T's network. So the high-level idea is you'd like to take a network that's in one configuration and then change it to a second configuration, like getting rid of that router that's going to go down for maintenance and changing from one set of forwarding policy to another. Ideally, you'd like to have the illusion you're making that change in one fell swoop. And that would be really nice, because if you knew that all the packets were either being forwarded the old way before the change or the new way after the change, if you wanted to know what was going on in your network, you could ask questions only about the before and the after and not have to worry about any interleavings of anything else. For example, if the old and the new policy avoid loops, you would know that you'd never have packets in loops. So it'd be really nice if we could have that abstraction and have the runtime system do the rest. So we don't want packets in flight that can be handled by a policy one in one switch and policy two in another. But now we've got a much better interface for doing this. We don't have to trick the routing protocols. We don't have to shove decisions down their throats. We can use an open interface to essentially walk the network through the intermediate steps that we want. And here's the idea, again, very simple, but this is simple is good here. The goal is not for these things to be complicated, it's for them to be right. So the idea was this: have every packet stamped with a version number as it enters the network, like a virtual LAN tag. All the policies in the network switches match not only on the other header fields in the packet, but also this tag. When it's time to update to a new policy, you install the new policy that will match on a new tag, but no packets are actually stamped with this tag yet. So these are unobservable updates to the network. They won't affect the handling of any traffic, or at least not yet. And then finally, only when that's completely done, go to the perimeter of the network and start telling the edge switches to start stamping packets with the new tag. Now packets will start being forwarded based on the new updates you've made. And after the packet's in flight, using the old policy of drained out of the network, you can safely remove the old rules in a lazy fashion because they're not needed anymore. And this is just one example. The way I described it sounds pretty expensive. You're going to have twice as many policies in the network as you have both coexisting at once. But in practice, you often are making a relatively small change to just a subset of the rules in the network. And there are a lot of variations on a theme here. Depending on what consistency property you want, you can have a different algorithm for how you do these kinds of updates. And in fact, there's been sort of a cottage industry of different kinds of designs of this type. So before I go on, this may be another good place to stop for questions. Anyone have questions on this portion of the talk? Okay, so next, OpenFlow started getting more widely used, and a bunch of use cases were studied both in an academic setting. Here are some that my group worked on, but many others too. And then a couple of use cases that ended up being killer use cases that came from industry. Traffic engineering, a problem that I'd worked on at AT&T, but has a completely new variant in the private backbones that large cloud providers like Google were running. And so Google has some really lovely work on using central control to do traffic engineering in their private backbone. And second, Nicira, who's a startup company acquired by VMware, also had a killer use case for supporting multiple tenants in virtualized data centers. And so we started to see cloud providers who were happy to buy equipment with merchant silicon chipsets, happy to write their own code rather than have the network vendors do it for them. And we started to see some of this technology get actually used in practice. So unfortunately, the story doesn't end there. The original design of OpenFlow was simple, the way I described it, but it unfortunately had a single rule table in the beginning with around 12 different actions you could do, 12 different headers you could match on, and a small number of actions, and a lot of policies that sent packets to the controller, which was a recipe for scalability problems and security problems. And so later versions of OpenFlow gradually addressed these limitations, adding more tables, more header fields, more actions, but it was never enough. It was like second system syndrome happening over and over again. The spec was getting longer, more complicated, and yet it was still not right. And so those of us working on OpenFlow began to worry, where does this end? Similar to the worries we had at AT&T when we kept making the control plane, the management plane more and more bloated. Now the OpenFlow spec is getting more and more bloated. Time for a change of a more fundamental nature. So people at Stanford and at Texas Instruments did some really exciting work looking at, now that we know that programmable networks are a good idea, what would we do if we designed the hardware with that in mind? If we weren't obliged to work with the merchant silicon chipsets, how would we change the hardware? And so the RMT paper, which was at SIGCOMM 13 from Stanford and Texas Instruments, looked at a performance first variant of active networking of sorts. Packets would come in, they'd be parsed, but the parser would be programmable. So you could decide which fields of the packet you extract and maybe define new header fields. And you could go through a pipeline of tables that match on packets, but the actions are now done by arithmetic logic units that are more general than the earlier designs. And there could be persistent state read and written as the packets flow through to affect the handling of the next packet, enabling much better network control and network measurement. But the key here is, although it was possible to make the hardware more flexible, it was done in such a way that it didn't affect performance and power and cost. And so it's constrained. And then we'll come back to that in the rest of the talk. These devices are programmable, but not arbitrarily so. Moore's law is almost over. And just as we see TPUs and GPUs in other contexts, we have these, our programmable packet processors, our domain-specific programmable devices for our use case that are taking advantage of the unique characteristics of what we do in the network, and also realizing that we may not be able to support general purpose computing at continually higher and higher speeds. So I was on the sidelines for this project. I wasn't involved at all, but I became really interested in what it would enable. And in particular, a group of us, the authors of that paper, as well as myself and others, started thinking, let's get the language right from the beginning. We knew that OpenFlow suffered for the lack of a linguistic formalism. What if we could combine knowledge of the hardware, knowledge of networking, and knowledge of programming languages from the beginning and try to get it right? And so the P4 language, which is what I still work on today, was designed with three goals in mind: to be protocol independent, so you could define your own parser and header formats and match action tables; target independent, so you can write programs without knowing the details of the hardware. This is something in regular computer science we've done for decades in higher level languages, but in networking is still relatively new. And finally, to be reconfigurable in the field. So you can buy a piece of equipment and make it act like a firewall today and a network address translator tomorrow and something else the next day. Now, in practice, I don't think we're done with this. Frankly, target independence is still a goal we haven't really fully met, and we're still struggling with that one. But we're making progress. So what have I been working on in this space? Well, I've always felt that knowing what's going on in the network is harder than knowing what to do about it. Once you know something is an attack, you block it. Once you know something is causing congestion, you reroute it. And so I've focused a lot on doing analytics directly in the switches as the packets fly by, to ask questions about the heavy traffic, the performance problems, the small timescale anomalies, and so on. Essentially looking at hardware efficient data structures that can run in the data plane, and collaborating a lot with colleagues in theoretical computer science who think a lot about sketches and compact data structures. And more generally thinking about systems we can build that will answer a broad range of questions about the network traffic and performance while working within these very, very strict constraints on how the hardware can perform. So in a way, if you go back to that control loop I've mentioned a lot of times during the talk, really here now the measurement and the analysis are combined together. Rather than the measurement being inside the device and the analysis being at a central server, we're doing the analysis in a customized way, customized to the task at hand, right as the packets fly by. So the analysis can be both efficient and fine-grained because it's customized to what you're actually trying to find out about the network and done where it needs to be done, right where the packets fly by. So more generally, and I'm going to skip over some of the details in this slide, we're looking at other use cases now that close the loop, that measure, analyze, and control directly in the data plane. And we've come back to those traffic engineering use cases I mentioned at the beginning of the talk, where we'd like to automatically route traffic on the least congested path, not using software, but doing it directly as the packets fly by, implementing routing protocols directly in this P4 language based on performance statistics we collect directly in the switches. Now, in the interest of time, won't go into all the details about that. But the reason I wanted to mention that example just briefly is I think a mistake earlier in my work was to think about the control loop as these three disjoint steps: measurement, analysis, or optimization and control. That was really born out of not being allowed to change the measurement, not being allowed to change the interface to the control, and having no choice but to do the analysis and the optimization outside of the network. And so as a result, we had separate abstractions for each of these three things. And even when we worked on OpenFlow, we still had only modest influence over measurement and control. And so these three steps had to be separate. But really the right way to think about it is to think about network intent. The network administrator should be able to say what their network-wide goal is and what constraints there might be. That I want to minimize congestion while still ensuring traffic goes through a middle box. Or I want to make this maintenance change without causing transient disruptions. And we should then have a compiler that will take those high-level goals and constraints and generate the device local programs. Now, if you talk to people in the networking industry, intent-based network management's all the rage. It's not a new idea. The idea that we should tell the network what to do and the network should just do it. But what's different here is that a lot of work on intent-based network management assumes that you have to work with the legacy routers. And I would posit, based on the work I did at AT&T and on OpenFlow, that if you're not allowed to change the devices, it's very, very difficult to raise the level of abstraction for running the network. But now we have the luxury, as the devices are programmable from top to bottom and from end to end, to put functionality where it belongs and synthesize it from above. This too is by no means done work. This is a really active part of my current work, is to think about how to specify high-level intent and how to synthesize the device local programs that are correct by construction in doing that hard work. So stepping back, over the last several decades, the community as a whole and myself in particular have been pushing, trying to get more programmability in the network, making the management plane programmable, gradually making the control plane programmable, and finally starting to make progress on making the data plane fully programmable. And in many ways, coming full circle back to the world of active networks from many years ago, with perhaps a heightened focus on being pragmatic. And perhaps now maybe the time is right. So I thought I'd just end by saying a few words about some sort of high-level lessons from this journey. One is, I mentioned early in the talk, is finding compelling use cases. And in particular, if there's somebody who's struggling, a network administrator, an application designer, and really deeply understanding their pain, you're bound to find something interesting to work on, something that other people are overlooking that can help that person not be suffering. A second is that a lot of networking problems are quite multifaceted and rich. They're often, frankly, I kind of think networking isn't really an academic discipline at all. It's really just a bag of hairy problems with technical constraints and a lot of other non-technical constraints as well. And so these areas like distributed systems, programming languages, architecture, algorithms, software engineering, all have something to tell us about how we can design and operate networks better. And also it's just a lot of fun to talk with people from different disciplines who haven't drunk your Kool-Aid yet and will ask really hard questions about the assumptions you make in your work. And finally, I'm going to sound like an old fogey now, but knowing some history, a lot of these ideas come around the pike many times in the early 80s in the phone network, in the active networks work, even in multi-computer networks. Different kinds of networks, different kinds of constraints, different moments in history with different opportunities to affect change. And so it's helpful, I know. In computer science, the field changes so fast, it's easy to think that papers from more than a handful of years ago aren't relevant, but it's often not the case because the problems and the constraints move around and often come right back to where they were. And then finally, going back to the very beginning of the talk, the two themes of, don't fight what you can't change. The way that played out in the talk is at the beginning, we really assumed we couldn't change anything about the equipment, the hardware or the software. Then we assumed we couldn't change the hardware, but we could have an open interface to it. And then we assumed we could change the hardware, but it still had to run fast and at reasonable power and chip area. So in each of these projects, there were constraints relaxed, but other constraints that remained. And they each spoke to the moment of what we really felt that we could actually change at that time. But the only reason progress was made in making more and more things open for change was the whole community working on building and deploying prototype systems, demonstrating the ideas, demonstrating that you could push the technology to the next level, getting other people on board, and doing the hard work of building community, both within academia and in industry, to try to have articulate a vision that's hopefully larger than any one person's research would be. So I'll stop there. I'd be happy to take questions. Want to thank a lot of people that worked on these projects. I didn't acknowledge a lot of the people as I went along, but there's a ton of people involved in many of these projects along the way. And also, of course, there are people in my current research group at Princeton. And I'd be delighted to take any questions.
Thank you, Jen. That was a great perspective. Actually, yeah, I think it was great to see how everything fit together so nicely in that story. I think Anna has a question.
I was curious for the story behind the AT&T Long Lines Department badge that you showed on the NCP slide.
Oh, yeah, that was just a logo that appeared in the Bell Systems Technical Journal. So I was just convenient to show it.
Was there actually a Long Lines department, or was this a joke?
No, there was. I loved at the Bell Labs cafeteria that there is also silverware from every different incarnation of AT&T, so you never knew which version of the company's fork or spoon you'd be using at lunch on a given day.
So I think Matt Johnson has a question. Matt, feel free to speak up, or if you want me to relay the question, I can do that too.
Thanks, Jen. This was a really great talk, and the perspective is really cool. I was curious if you had any thoughts on the challenges or opportunities to putting any of these ideas into practice with like public networks with multiple entities, or where you're involving multiple organizations and trying to define and implement these rules.
I'm really glad you asked that, actually. So there are a couple of answers there. I think it's obviously harder in that context when you have to get some sort of agreement. One use case is exchange points. So there are these places on the internet where multiple content and service providers meet. And those become really natural places to put programmability because you can put a lot of functionality at the juncture point between these networks. And that becomes also potentially a value-added service that those exchange points can provide. And a second thing is, I think, the internet's, because of so much industry consolidation and so much replication of data centers and of content, that now we're often in the case where the traffic only goes through maybe two entities, sort of the content network and the eyeball network. And so I think the level of cooperation you would have needed, 10 years ago to have end-to-end programmable control has really collapsed, where you can actually have end-to-end control with maybe two parties collaborating. And so we're not there yet. I wouldn't say that that's actually happening in practice yet, but I'm more optimistic because you don't really have the sort of 6 hops through 6 different networks to have to convince to all upgrade. You can often maybe get Google and Comcast or Microsoft and AT&T, and that can be enough to start doing something interesting. And in fact, if you go fast forward to 5G, where you might even have the cloud and the access network together, you may even have one network that has got everything end to end in it, where you can start to put programmability. And that's an area I've been starting to learn more about recently.
So that's kind of interesting. I think one way I kind of wonder your thoughts on it, like, I think suppose you had all the programmability, one kind of, blue sky question you might ask is, what is the goal of the network? If you, from your perspective, were giving us, revising that old classical paper about the internet design principles, what would you now say, knowing what we know now, if you were designing networks from scratch, what would be the top 5 goals the network should have?
I think it's going to depend on the setting. So it's kind of an evasive answer, but I think it's really true. I think in some settings, you're going to care much more about security and anonymity, and others you're not. So it'd be great if the same programmable substrate could handle multiple points in the design space, and that we understood how to do that. I think another problem is now throughout the talk, so much of the work was putting functionality where we were allowed to put it. And we don't have any sort of science of saying where we should put it. And sometimes you put it in one place because the hardware is not capable or the interface isn't open. But now we do have an open interface, and it makes it actually quite hard to say, which kinds of things belong where. It's a different question than you're asking, but I think a related one, because you would hopefully like to be able to go from some high-level goals to some low-level realizations of those goals. But if we don't even know how to reason about division and placement of function, we still have a long way to go, I think, to bridging that gap.
I think that's fair. Sometimes I kind of think about, can we just run machine learning on network architecture, right? Right. At the end of the day, it's a design space you can search through.
Yeah, exactly.
Yeah. Anna?
To follow up to what you and Ratul were talking about, as you're thinking about where do different services go, I'm also wondering who is going to be writing these programs on the network. Does it remain really the network administrators? Does it become folks who are doing larger data center work, sort of in the system space? Will the people who are actually, renting their little spot in a data center want to be writing programs on the network? And if so, how would we support the different levels of both access and expertise?
Yeah, that's a great question too. I think, first of all, writing programs in P4 is really hard. So it's definitely a high barrier to entry. I mean, being an open language doesn't make it easy. So raising the level of abstraction for programming the network is useful, not only because network administrators should operate at a higher level, but probably most people shouldn't be writing P4 code in the first place. That said, I will say the existence of P4 and also software platforms that others have built, like Mininet and others that have come out of Stanford, it now is the case I can have an undergrad do a semester project where they build an app. And that's actually something, a decade ago, networking students could only read qualitative text. and try to think about what the network should do. Now you can actually at least try stuff out. But in short, I think if you look low in the stack, I hope that there become sort of a standard set of libraries. There are places in networking that are not differentiating, where you would think many companies will have similar needs. Basic telemetry of what's going on in the network, traffic engineering, and so on, where you would hope it's open source and that's fine, because hopefully there's not so many ways to do it, and it's not going to be what makes one company competitive with another, and that they'll compete higher up the stack. And ironically, open interfaces help there to allow people to build proprietary solutions higher up the stack without having to get the vendor in the loop on helping them do that. So I think we'll hopefully see a portion of the stack that is open source, because it's just not, it's not that it's not technically interesting to us as researchers, but that hopefully it's not where the product differentiation will actually happen, and stuff higher up that'll be more differentiating.
Maybe this is more of a comment than a question, but I kind of emphasize that, I recall 20 years ago, roughly at the same time Jonathan was doing active networks, and the same was David Weatherall, that people would actually write papers saying, oh, of course it's absurd that you would be doing any kind of computation on every packet, that it would be impossible to even imagine doing that.
Mm-hmm.
And so one question is, so over that 20-year period, we're clearly different from that.
Right.
And possibly they were wrong then. Like possibly the issue wasn't really that it was programmable or not. What the issue was, they thought certain types of computation were okay, like longest prefix match. Somebody wouldn't have decided to, when they were designing the system, like, oh, that makes sense to do on every packet. Like, of course, that's going to be easy. This is this multi-level tree lookup that has to happen on every packet that gets routed through the internet. Or maybe it's that actually there's been this technological shift of how much computation we can do per communication that over time has led us in this direction. I kind of wonder though, during that period, even though Nick McKeown ends up being part of this push towards programmability, I remember him even a decade ago coming in sort of exactly this setting, arguing that, yeah, we're going to need to do optical switching to be able to keep up with speed. So I don't know, maybe looking forward, is it the case that we're just at a sweet spot now where we can do computation, and we're about to move into a world where, in order to keep, part of the argument you made is, okay, you can't compromise on speed, but as long as you don't compromise on speed, you can do anything you want. It's much more powerful if you can do computation on. So anyway, I don't know if you have any speculation, at least on, maybe I've now set it up so you can't speculate because you'll almost guarantee to be wrong.
Yeah, I don't know if I have a deep answer there. I do think part of the bottlenecks on switches, the switch data plane, has shifted, where it's really about the speeds and feeds getting in and out of memory and across the pipeline. And putting a programmable ALU and a programmable parser doesn't really fundamentally change that math very much. And so I think I would flip it back around. I think the programmability that's there in these programmable data planes is the programmability that's cheap to add, because it's already, it's not in the place where it's most expensive. You still can only do a small number of memory accesses per packet. That didn't change. Many of devices had programmable parsers before just to be future-proof. They just weren't open to the programmer. They were just used by the vendor to future-proof their equipment. So in that sense, I don't think anything that's happened now contradicts what you've said. It's more that I think in the early days of active networks, the vision was for a much richer programming model. And in a way, when we came full circle, it's actually much more modest. And I think that, right, and also domain-specific processors have become a thing, right, where we've learned how, the royal we, the hardware people have learned how to do domain-specific processors so that we can crank up the speed by customizing the hardware rather than trying to stay Turing complete. And so we're getting some extra mileage out of that aspect. But you're of course right. There's going to be some speed at which we're not going to be able to be programmable enough to be interesting. And maybe in that part of the network, we will just use optical. I think it's not an unreasonable point that there'll be parts of the network where we can have arbitrary CPUs doing programmable functionality. Other places you'd want a P4 switch, and other places you'd want nothing. because the speed's just too high.
There's this analogy with RISC computing where it ended up, we run RISC computers as the microarchitecture for all computers, even though the interface to them is not RISC. Anyway, this question of like the other side of it, right, is that it seems like we're at this inflection point where, Moore's law and Dennard scaling is really like, run into a wall, but optical, bandwidths continue to skyrocket, right? They're still on an exponential growth path. And
yeah,
that suggests that, we come back 5 years or 10 years from now, we're like, oh, like how are we ever going to be able to make, 10 terabit networks work, when the chips that we're using for switching them are still, have the same kind of constraints that they have today. So.
Yeah, I think that's quite fair. In which case the programmability might be more at the edge, in the NIC or in the access network and not necessarily in the core.
So as fascinating as this discussion has been, I think our AV host has just reminded me Jen's on the East Coast. So we should really let her go and hang out a little bit with her daughter. Thanks a lot, Jen. This was a great talk. I think I really enjoyed it. I hope everybody else did too.
Thanks so much. It was really fun.
Yeah.
Look forward to the time we can do this all in person.